Alright, so the reason we started with this unit and factoring is because we have to be able to factor in order to do this next part, which is graphing polynomials. So standard is I can graph cubic and quartic functions by hand. And the for application is ones that cannot be factored. You're also able to graph those. So you now have the skills necessary to attack the standard. With any graph we have dealt with so far, we have referred to the most important points. These points are our max and mins. We also have referred to x-intercepts as most important points. In order to graph cubics and quartics by hand, we need these points. Some of them you will find through factoring and others with the table of values. We're going to look at a few examples together after going through the general steps you need to follow. Now I'm going to suggest that you pause the video at this point so you can copy down the steps, and then I'm going to go through them. Alright, so the first thing is to determine the end behavior. Now the end behavior is basically saying, okay, on the left part of the graph is headed this way, it's either headed down or up. On the right hand side, you're either headed down or up. So the two scenarios that you'll have is if you have an odd degree, which is like a cubic or a quintic. If you have a positive leading coefficient, so the LC means leading coefficient. That's the fancy word for saying the first number in your polynomial. If you have a positive one, then that means as you progress, as your x gets bigger, so as you go from left to right, on the right hand side your graph has to be headed up towards positive values. So if you have a negative leading coefficient, it does the opposite. As you go left to right, you should be headed down towards negative values at the end. Even degree, like quartics and quadratics, and behavior will both be going up. For example, like if a is positive in a quadratic, you're both headed up, or they're both headed down. So you factor and solve to find the x-intercepts. This is exactly what we did in the last standard, just yesterday. Find a table of values, which we'll talk through, and then graph and give the domain and range. There are two identifiers to any polynomial that will tell you a lot about what the graph should look like. These identifiers are the degree and the leading coefficient. Now, I already kind of talked about it up here, but that's pretty much the discussion on the effects. So if you have a positive leading coefficient, you have an odd degree, an even degree. Maybe you want to add in here that this is a cubic, this is a quartic or a quadratic. If you have a positive leading coefficient, it's going to go down on the left. Your graph is going to be headed towards negative values on the left and positive values on the right. If you have a negative leading coefficient, it does the opposite. And then even degree, they both go up or they both go down. So when we actually start graphing, you'll see me draw in some arrows at the very beginning so that we know what my graph should look like kind of at the end, or at least what direction you should be headed in. Okay. Let's go ahead and flip. So example 1, graphing polynomials. First thing we're going to do is determine the end behavior. So we have a positive leading coefficient and it is a cubic. Since it's a cubic, that means the end behavior is opposite. And since this is a positive leading coefficient, that means on the right hand side I'm going to go up and on the other side I'm going to go down. Okay. Then we factor and solve. So I'm going to set this equal to 0. Now, to factor and solve this, looks like the pattern for the difference of cubes. So that's what I'm going to do here to factor. My a is 5x, my b is 2. So I get 5x minus 2 times 25x squared plus 10x plus 4. Now with these type, when you factor and solve, keep in mind that every time we factor and solve using this pattern, the answers here are always going to be imaginary. So since I'm trying to solve and actually plot the answers that I want, or that I get on the x-axis, I'm going to just cross that off at this point. I'm not going to solve because I know my answers are going to be imaginary. So I know my only x-intercept is going to be 2/5, because that comes from that factor there. So then I'm going to go ahead and plot 2/5. Now, because I have only one x-intercept, and I don't have really I don't have any turning points, because basically what's going to happen is your graph is going to start down here, it's going to curve up towards positive values. But the only place where it connects to the x-axis is that 2/5. So to find other points that I can plot to help guide my graph, I'm going to pick one value to the left and one value to the right, and I'm going to make them easy values. So 0 and 1. If I plug in 0, I get -8. If I plug in 1, I get 117, I think. Yep. Now, since this is so large, I'm going to make each box on my y-axis worth 10. So 0, -8, going to be right there. And then 1, 117, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we're going to go ahead and connect. Okay. So since this is a cubic, it's not going to look like a line because it is going to have a slight curve to it. But a lot of times when you have to use a pattern, a factoring pattern, to get your x-intercepts, your graphs look like this because there's only one x-intercept. Okay. Here's another one. This one is going to open, not open. This one is going to have the same end behavior as example 1 because I have a positive leading coefficient and an odd degree function. And then I set this equal to 0 and factor. Now, in this case, this doesn't look like a difference of squares, even though I only have 2 terms. So I'm going to start by pulling out the greatest common factor. Okay. Now, when I set these equal to 0, I get 3 as an answer, and I get 0 as a double root. Now, in quadratics, when we got double roots, we knew that that meant that this is a vertex. This is going to act the same way. When you have double roots, and maybe you want to star this or circle it or something, that means my graph is going to touch but not pass through. So I have an x-intercept at 0, and I have an x-intercept at 3. But that means when I get to 0, my graph gets to 0 because it's going to start down here in the negative. It's going to come up, it's going to touch at 0, but it's not going to go through. So it's just going to touch and act like a vertex. So it's going to bounce off, come back down, and has to loop back up to go through the last x-intercept. So we have one turning point we have to find. The turning point, since it only touches at 0 and comes back down, is going to be halfway in between these two x-intercepts. So I'm going to pick halfway in between, 1.5. And then I'm going to store 1.5. And then plug it in. And I get -3.375. Then this I'm going to plot. And that's enough to draw on my graph because it gives me a turning point. So I'm going to go up, touch, turn, and go through the last x-intercept. Now, in both these cases, we didn't talk about the domain and range. But because a cubic will continue on forever and ever in this way, and it'll continue to grow slightly in this way, it's going to eventually cover every x value and every y value. Same thing with this one. So with cubics and quartics, your domain and range will always be all reals. You can plug in any number you want, and you can also get out any number. Okay, go ahead and flip. Okay, here's another one. Positive leading coefficient, odd degree. So there's my in behavior. Then I'm going to set this equal to 0. And solve. Now I have 4 terms here. So I'm going to start by factoring grouping. I can pull out an x squared. Here I can pull out a -1. This is a situation that's not completely factored because this is a difference of squares. So that's going to break up into x plus 1 times x minus 1 times x plus 2. So my 3x intercepts are going to be -1, 1, and -2. So I'm going to go ahead and plot those right off the bat. And we'll talk about the graph. Okay, so the graph is going to come up from negative values because of my end behavior. None of these are double roots, so it's going to have to pass through each of them. So it's going to come up, pass through, turn again, and pass through the last one and be headed up towards positive values. So I have two turning points. I have this one, and then I have this one. So I have to, in my table of values, find the halfway point between -1 and -2, which is -1.5, and the halfway point between 1 and -1, which is 0. Well, when I plug in 0, that one's easy. I just get -2. When you plug in -1.5, let's actually do that one. You get 0.625. Okay. So -1.5, 0.625 is going to be really close there. And then 0, -2. And then we can draw my graph and connect my dots. There we go. Okay. I think we have time for one more. Let me just double check. Yep. All right. So with this one is a quartic, so it's an even degree. Oh, sorry, domain and range should be all rails. So because it's leading coefficient and it's an even degree, my end behavior is going to go up and up. Then I'm going to factor. Now, thankfully I can plot a greatest common factor here of 2, or you can think of it as dividing everything by 2. And you get this expression. And then I can factor that, like I would a normal quadratic, and look for two numbers that multiply to get 36 and add to get -13. And those two numbers will be -15. Whoa, that was wrong. Those two answers will be 9 and 4. Both of them negative. And both of those are difference of squares. So I get these four expressions. So -3, 3, 2, -2. And I'm going to go ahead and plot those. Okay. And then we're going to make a small table of values, which I've run under from here. Now if it goes up and up, that means it's going to come down, loop, loop, loop. So I have three turning points. I have this turning point, I have this turning point, and I have this turning point. So I need the halfway point in between -2 and -3, +3 and +2, and then 2 and -2. So those are the 3 points I'm plugging in. Now because I have more than one point, I went ahead and put my equation into y equals, and I'm going to use my table here, so -2.5, 2.5, and 0. So I get 72, -12.4, -12.4. And I'm going to go ahead and make my y scale worth 10. So -2.5, -12, +2.5, -12 point whatever, and 0.72. 1, 2, 1, 2, 3, 4. And then connect. Okay. And I think we have time for this last one here. Now, this one, the end behavior is going to go up and up. But when we go to solve it to try to factor, there's now two numbers that multiply to get -5. And and add to get positive 6. So this one is not factorable. If that happens, then you need to resort to a table of values. And if you do that, I would highly suggest going to your calculator and using the table feature of your calculator. Oops. Oh. And then I'm going to go from -3 to +3. Okay. You can see it's very symmetrical, which is nice. Okay. Then the last thing you have to do here is draw these points or plot them, and then connect with a smooth curve. Alright. I think that's it for today. I want you to do that part on your own. Actually plot these points and graph it on your own. And we'll check it tomorrow. Alright, this is Crisscross signing off.